Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or even a comment. It's totally free for you, but it really means the world to us. Let's keep leveling up together. Today, we are undertaking, a really deep dive into the engineering paradox of uptime. We're dissecting your sources on maintenance strategy and redundancy design. And our mission is to answer one single critical question.
Which is?
When does all that effort to increase reliability, all that extra maintenance, those backup systems, when does it actually harm your bottom line or maybe even more shockingly, increase your overall risk?
Yes. It's that moment every engineer has, I think, where you realize the core lesson of reliability is that perfection is just unaffordable. And a lot of the time, it's actively counterproductive.
Right. We're taught that robust systems need more and more preventative steps, more hardware.
But the true optimization sweet spot is it's rarely at the maximum level of complexity.
So we're going to be dismantling the myth that more maintenance always equals more reliability. We'll explore when run to failure is actually the smart, correct strategy, and why that expensive redundant system you just budgeted for might fail exactly when you need it most.
So where do we start?
Let's start where every good engineering decision should start, with the finances. What is the true cost of ownership?
Okay, so we have to define life cycle costs, LCC. If you don't track the whole picture, you're really missing the point of optimization.
Right.
Your sources break LCC down into four major areas.
Why?
First, you have acquisition. That's the capital, the installation cost.
The sticker price.
The sticker price, exactly. Then second, ownership. This is the big maintenance bucket. It covers your planned preventative work and all the unplanned corrective repairs, plus modifications.
Okay.
Third is operating consumables, energy, materials. And finally, administration. All the documentation, data acquisition, the bureaucracy of compliance.
And inside that ownership cost, that's where we find these two variables that often get confused: reliability and maintainability.
Oh, all the time. They are not interchangeable.
So break that down for us.
They're deeply connected, but they serve different masters. Reliability is a measure of how often something will fail. It determines the frequency of your repairs and, therefore, how many spares you need to keep on the shelf.
Okay, so how often it breaks. What about maintainability?
Maintainability is how quickly you can get the system back up after it fails. It influences training, test equipment, manpower, and that crucial metric, mean time to repair, or MTTR.
So to put an analogy on that for you, the learner, reliability is how long your car goes before it breaks down. Maintainability is how fast the mechanic can find the faulty part and swap it out.
Yeah.
It's all about minimizing that downtime.
Exactly. And when you factor in the financial hit of that downtime, the lost revenue, you see why both are just as critical. But if we zoom in on the cost of not focusing on them early on, the numbers are, it's staggering.
Staggering is absolutely the right word. Look at the failure data from that key UK industry study cited in our sources. They found that failure costs, so that's rework, scrap, warranty cost, all of it, accounted for about 18.1% of the total quality cost.
Just stop and think about that number. 18.1%. That means nearly a fifth of your total quality budget is being spent just fixing screw-ups.
It's pure waste.
Pure waste. They quantified it across the industry. It resulted in a loss of approximately 6,000 million pounds in defects and failures in a single year. That is a massive sunk cost of inefficiency.
6,000 million pounds wasted. That's the premium you pay for getting the design wrong. Now compare that to the cost of prevention.
It's not even close. Prevention costs, things like design reviews, quality planning, training, they're typically only about 1% of the total quality cost.
1%.
1%. You put in a pound of prevention, you save multiple pounds of failure. If you can make a small, focused investment up front, say 1.5 thousand million pounds across the industry, and you only cut that failure bill by just 10%.
You immediately release 600 million back into the economy.
Exactly. It just proves that optimization is fundamentally about prioritizing those small, upfront investments.
Okay, so once we've paid that prevention premium, the next step is making sure that when something does fail, we can fix it, and fix it cheaply and quickly. This moves us squarely into optimizing the maintenance strategy. When is the right time to actually open the hood?
This is where we shift focus from reliability, preventing the failure, to maintainability, reducing that MTPR. And Most people assume maintainability is purely about how good your technician is.
The skill of the person with the wrench.
Right. But the reality is the physical design of the equipment heavily, heavily dictates the MTTR. You can actually use checklists to score a design and predict how long a repair is going to take.
That's fascinating. So what kind of things are on these checklists? What design choices save minutes versus costing hours in the field?
Well, the devil is always in the details of access and tools. Always. For example, a checklist scores access critically. It asks, is the access adequate for just visual inspection?
You can see it, but you can't touch it.
Exactly. Versus access that's adequate for manipulative actions. Can you actually get a tool on the bolts? Can you replace the part without dismantling the 5 things surrounding it? If you can't manipulate it, your MTTR is going to skyrocket.
And I love the criteria around tools.
Mm-hmm.
We've all seen equipment that needs some proprietary wrench or a bizarre setup.
Oh, absolutely. The checklist immediately flags a design deficiency if you need special tools or custom jigs. And this includes basic things that engineers, we often overlook, like needing a stepladder or a dolly just to reach a component.
Zip ladder.
A stepladder. If your repair tech needs a stepladder to replace a component, your design for maintainability has already failed. You've baked that complexity right into the system.
That instantly identifies the root cause of every angry field service call I've ever taken. So we fix the hardware design, we make it maintainable, but then we hit the second problem, the data. You need good data to know when to maintain something, and collecting it is incredibly tricky. I want to highlight this problem of recording non-failures.
This is such a silent killer of reliability models. A non-failure is when a component gets removed because it was suspect.
So it hadn't actually failed.
No. Maybe it was dirty, or a scheduled overhaul was due, or just looked funny. But it was still working. If that component gets logged in your system as a failure, you artificially inflate the perceived failure rate of that part.
And what's the consequence of that inflated rate?
It completely skews your reliability predictions. It leads you to perform unnecessary preventive maintenance way too early, and you just burn through your spares inventory because you think parts are failing faster than they really are. You're replacing perfectly good components because of paranoia manufactured by your own bad data.
And the other side of that coin is inconsistency, especially with components that wear out. Let's say you have a pump that's 10 years old, but a critical seal inside it was replaced last year.
Right.
If that seal fails today and you record it as a 10-year failure, your data is corrupted.
Precisely. You need a consistent tagging system, unique tag numbers, to accurately date when an item was installed or refurbished. For that seal, you have to track the time to failure from last year's installation, not the pump's original 10-year service date. Without that kind of surgical precision in your data, your whole maintenance strategy just collapses.
So we have robust maintenance, we have pristine data. Now we look to the final piece of the uptime puzzle, redundancy, which brings us to this big reality check.
In theory, redundancy is simple. You can contrast it with a simple series system, where if any single block fails, the whole system just stops. That's modeled by the OR gate in a halt tree.
We all get the OR gate.
Yeah.
But with parallel redundant systems, the math changes to the AND gate. Failure only happens if all the blocks fail. So that should drop the failure probability to near zero. Why doesn't it? Why do our duplicated systems so often fail to deliver?
That expected drop-off in failure rate is completely undermined by one thing. The common cause failure, CCF.
The unforeseeable event.
Exactly. It's the single factor external to the primary failure mechanism that defeats the entire redundancy at the same time.
Give us some hard examples of CCF, because this is where a huge capital investment can become completely worthless.
The vulnerability is always from shared infrastructure. A classic CCF is a shared power supply. 2 redundant servers fail because the single circuit breaker feeding them both trips. Or a single environmental event like a fire or a burst pipe affecting multiple units that are physically right next to each other. And this is so crucial for the modern world. Duplicating hardware with identical software is zero defense against software failures.
Say that again. That's huge.
Redundancy only protects against random hardware failures. If the same coding bug exists in channel A and channel B, that bug is the common cause. The whole system fails the moment that bug gets triggered.
So that means if I buy 2 identical systems, load them with the same software, I'm paying twice the capital cost for effectively zero improvement in software reliability. It's a brutal lesson.
It is, and we have tools to quantify just how likely these CCFs are. We use methods like the beta factor, which assesses this susceptibility. For systems with redundancy with identical channels, your exact scenario, a frequently used beta value, is 20%.
Wait, You're telling me that just because the channels are identical, the system automatically has a 20% inherent likelihood that a single common cause will defeat the entire setup?
Precisely. That 20% is a built-in handicap before you even analyze specific shared pipes or power rails. It represents the probability that the failure mechanism itself, environmental, maintenance-induced software flaw, will just bypass the redundancy.
So what's the defense?
Diversity. Use different technology, different software, or critically robust physical separation. If you can't diversify the design, you have to physically separate the channels.
That 20% figure is a massive wake-up call. But if common cause failure is the unforeseen event, our final topic addresses the most common and, frankly, predictable cause of failure. Us, the human element.
When you connect these technical models back to real-world catastrophes, the pattern is just undeniable. Flixborough, Piper Alpha, Chernobyl, these didn't happen from random equipment failure alone. Human factors, errors in maintenance, or bad operating procedures played a dominant role in either starting the disaster or making it much, much worse.
Which means we have to quantify the human failure rate just as rigorously as the component failure rate. You can't just hope for the best.
No, you can't. And engineers use methodologies like the Human Error Assessment and Reduction Technique, or HART. This framework starts by assigning a basic error probability based on the complexity of the task itself.
Give us a sense of that scale.
Sure. A highly familiar task, performed by a well-trained person, might have a tiny error probability, say 0.00004. But a complex task, one that requires a high level of comprehension or an unusual skill, starts with a much higher base probability, maybe 0.16.
16%. A 16% inherent chance of error just based on the task.
Right out of the gate. And then it gets worse.
Because those base probabilities get modified by what's happening in the real world.
Correct. The base rate is then multiplied by factors related to error-producing conditions. This is the human reality. Inexperience, low awareness of risk, conflicting objectives like pressure to save time, they all have multiplication factors. For example, a technician operating under low awareness of risk might multiply that base error probability by a factor of 4.
Wow. So what's the engineering implication when you plug that final, potentially huge human error rate back into your system models?
If you run your fault tree analysis and the probability of a human making a mistake completely dominates the overall system failure rate.
Meaning it's more likely someone hits the wrong button than the button itself failing.
Exactly. If that happens, then remedial action is desperately needed. You have to change the operation or the design to either simplify the task so error is impossible, or just automate it entirely. Otherwise, your theoretical uptime is irrelevant. A tired or rushed operator will compromise it every time.
This has been an incredibly detailed and frankly sobering deep dive. So let's bring it all back to the central takeaway for you, the designer or engineer listening right now.
Optimizing system uptime isn't about simply doing the most maintenance or adding the most hardware. It's about minimizing failure costs by focusing on 3 areas. First, maximize those prevention investments early, where they save the most.
Second, aggressively simplify maintainability. Reduce that mean time to repair.
Yes, get rid of the stepladders and special tools through smart design. And third, critically evaluate your redundancy against the very real risks of common cause failures, and, most importantly, model and mitigate human error.
Which brings us to a final, provocative thought that really underlies this entire tension in safety and reliability engineering. Our sources discuss the perception of risk, differentiating between intolerable, tolerable, and acceptable risks, especially for fatalities.
We use quantitative measures, costs, probabilities, to determine risk. But the public uses emotion and perception. Think of it this way. Our sources show we tolerate you having a 1 in 1,000 chance of a fatal injury every year when you voluntarily drive a car.
That's an accepted risk.
It's accepted. But if you live next to a chemical plant, an involuntary hazard, the acceptable risk level is drastically lower. That risk must drop to perhaps 1 in 100,000 per year. And the tension for you, the engineer, is monumental.
So the question is,
how do you balance the quantifiable, often extraordinarily expensive cost of reducing a risk into that tolerable zone against the public's emotional demand for absolute safety from involuntary hazards? This huge gap between voluntary risk tolerance and emotional perception of involuntary risk, that is the ultimate balancing act in engineering practice. Think about that trade-off the next time you design a safety system.